Welcome to CX1104, Chapter 6.3.1. Today we'll continue with the topic orthogonality, and specifically we'll focus on QR using Gram-Schmidt. What is QR? In the previous chapter, we are given a matrix A, and we can decompose into two matrices, a product of two matrices Q and R. And this decomposition in the literature is called the QR decomposition. We'll now talk about the properties of Q. The first property, important property you have to realize is that the column space of A will be the same as the column space of Q. In fact, Q will be derived from A, and the columns of Q will be taken from the column space of A. In addition to the column space, it has other properties. QTQ will be the identity. What does it mean? It means that the columns of Q will be octonormal columns, and these octonormal columns spans the column space of A. QQT will also be another square matrix, but it might not be the identity if Q is not square. So one of the important remark is that Q may not be square, and hence QQT will not be I. QTQ is I, but QQT may not be I. In fact, it has a name, which is the projection matrix into the column space of A. We'll now talk about R, the second matrix associated with the QR decomposition. R is a square upper triangle matrix. And depending on A, if A has independent column, R is invertible, and if A has dependent column, R is not invertible. Alright, so let's see the Lay's theorem 12. In Lay's theorem, please remember that Lay has only stated this theorem for independent column. Let's see what happened for independent column. If A is a rectangle matrix m by n with independent column, so this QR factorization theorem only applies for independent column, then A can be factored into QR. Q is m by n, and if m is not equals to n, then this will be a rectangle matrix. Now this m by n have octonormal columns, and the columns of A is spanned by column of Q, while R is a square upper triangle invertible matrix. So here it is restating what we have just stated. We can write it in this way. The columns of A is here. We have n columns, so this is m rows and n columns. Now, when we write in QR, and remember Q, if we now write it as Q1, Q2, and Q, how many would there be? There will be n of them, n columns. This is m rows and n columns for Q matrix. And while in the R matrix, it will be n by n. And the nice part about this being an upper triangle is that this part will be 0, and only these values are filled, and including the diagonal elements of the R matrix will be non-zero. There are many motivations to perform QR decomposition. One of them is to solve the least squares. So in the previous chapter, we have already seen this. Let this be the equation we are interested to solve. We are given the matrix A, or we are given systems of linear equations, and we form A. We set up the equations into a matrix form. We have AX equals to Y, the right hand side. We perform QR decomposition to let A equals to QR, so we get QRX equals to Y. And remember the property that QTQ will be identity. We multiply both sides by QT, And then we will reduce this to the identity times Rx equals to QTY. Now, why do we go into one big round to solve for x in this way? Because we still have to solve for x. X is still unknown. What is interesting now is that this is the upper triangle. And this upper triangle can be easily solved Rx because we can do back substitution. Okay, so this is one of the reasons why we have used QR, and QR is popular. Now, in the coming slides, there are many ways to solve for QR decomposition. We'll only introduce the Gram-Schmidt auto-normalization to get the Q first, and then R will naturally come out. For references, you can look at the UCLA PDF, and as well as some data science YouTube video.